Hi, everyone. This is Unit 4, Population Proportion Estimation and Inference using Bayesian Approach, Part 3. Before I start, I would like to let you know that I did a little mistake in Part 2. So if you can find that, please let me know. I will reward you. So again, this is Unit 4, Population Proportion Estimation and Inference using Bayesian Approach. Part 3. In Part 1, we drove the posterior distribution under uniform prior when we have no information available about the population proportion. There is no previous information. Or as a researcher, I cannot add any information to the prior. There is no available information about pi. So we use uniform. And we found it is beta distribution with alpha, number of successes plus 1, beta, number of failures plus 1. And then in Part 2, we drove the posterior distribution under a conjugate prior. When we have some information and we would like to add this information to the estimation and inference about the population proportion. So we can, I showed you how to use a previous study to find alpha and beta for a conjugate prior beta distribution. And we found that the posterior distribution is also beta distribution with alpha star, alpha plus y, and beta star, beta plus n minus 1. In this part 3, we need to go over some other Bayesian estimation or point estimate. I know we covered the posterior mean, but there are some other point estimate we are interested in. Maybe we are interested in the posterior median, posterior mode, posterior standard deviation, posterior variance, and so on. And also we need to cover the inference. In frequency approach, we calculate confidence intervals. So in Bayesian, we calculate something called credible set to be able to say with probability, some value, the population proportion is between these two values. That's the statement that the frequency approach cannot make. And also, if we have H0 and H1, how do you decide which one is correct based on Bayesian approach? So we need to cover this one also. In frequency approach, they calculate something called p-value. And then based on the p-value, they see the data support H0 or support H1 or HA. So let's start by the estimation. The posterior distribution has all the information we have. So this posterior distribution has all the information that the previous study and the current data and everything. So all Bayesian estimation and inference is based on that. The graphical representation is fine, but it is not everything we need because we need to have some numerical summary. We need some numerical summary like the frequency approach, like mean, median, mode, standard deviation, 5-number summary, and so on. So everything will be based on the posterior distribution. And also to estimate a credible set, which is the Bayesian confidence interval, for the population parameter or do test of hypothesis, the posterior distribution is used also. So the posterior distribution will be used to do anything you want. The posterior mean is often used as the Bayesian point estimate of a parameter. And if we use the beta prior and the binomial likelihood, the posterior will be beta with alpha plus y, beta plus n minus y. So this one is alpha star, can call it alpha star, and this one beta star for the beta posterior distribution as beta. So the posterior mean is alpha plus y divided by alpha plus y plus n minus y, which is alpha plus y divided by alpha plus b plus n. So if I collected data, I know n, I know y. If I assign some beta distribution with some alpha and beta, plug in alpha and beta, and then you find the posterior mean. For our motivating example, n is 50 and y is 7. So let's plug in 7, plug in 50. And if we use the prior distribution as beta with alpha 10, beta 40, alpha 10, beta 40, you can find the posterior mean is 0.17. If we use the uniform distribution as a prior, what is the posterior mean of pi? Is it different from the maximum likelihood or it is not different? So if we use the uniform distribution as a prior, if we use the uniform distribution as a prior, the posterior distribution will be beta with number of successes plus 1, so it is 8. Number of failures plus 1 is 40. Number of failures is 43, so plus 1 is 44. So the posterior mean will be alpha. This one is alpha star, beta star. It will be alpha star divided by alpha star plus beta star. This one will be some value. You can calculate it. So it is different from the maximum likelihood. It is different from the maximum likelihood. So why? This is a question I asked you last video. So if you know the answer, please let me know. I will reward you. So notes on the posterior mean. It is always between the prior mean and the maximum likelihood estimation. So let's see. The prior distribution is beta with alpha 10, beta 40. And the prior mean is 0.2. And the maximum likelihood estimation is y divided by n, so 7 divided by 50 is 0.14. And the posterior mean is 0.17. You see the 0.17 is between these two values. Is it always correct? It is always correct. The posterior mean is always between the prior mean and the maximum likelihood. Why? Because actually we can write the posterior mean as a weighted average of the prior mean and the maximum likelihood estimation. We can write this one, posterior mean, as a W some weight times alpha divided by alpha plus beta, which is the prior mean, plus 1 minus the weight times y divided by n. This is the maximum likelihood. And the weight is alpha plus beta divided by alpha plus beta plus n. So see, the posterior mean is always a weighted average of the prior mean and the maximum likelihood estimation. This is why 0.17 is between 0.14 and 0.2. But sometimes we are interested in the posterior median, posterior mode. So our posterior distribution is beta. So if you'd like to calculate the mode, it will be alpha minus 1 divided by alpha plus beta minus 2. If you'd like to calculate the posterior mode, it will be alpha star, beta star. If you are interested in median of the beta distribution, the median of beta distribution in general is alpha minus 1 divided by 3 divided by alpha plus beta minus 2/3. If you are interested in the posterior median, this one will be star, will be star, will be star. So everything is known. You don't need to work with the function itself. You need to be familiar with the formulas of the mean, median, mode, standard deviation, variance for the distribution you are working with. So for our case so far, we work with the beta, so you need to know everything about beta distribution. The posterior mode estimation under beta 1040 and 7 successes, 43 failures, it will be this formula. So it will be 0.16. So far we calculated the posterior mean and we found it is 0.17. We calculated the posterior mode, it is 0.16. So what about the posterior median? You can calculate the posterior median. So let's calculate the posterior median. Posterior median under beta 1040 is beta distribution with alpha star 17, beta star 83. So this one is beta star, this one is alpha star. So now I can calculate the posterior median. Posterior median equal alpha star minus 1/3 divided by alpha star plus beta star minus 2/3. I know alpha star is 17 minus 1/3 divided by 17 plus 4 plus 83 minus 2/3. This value is 0.1678. So you can use this estimation for the population proportion. You can use this estimation for the population proportion. You can use the posterior mean 0.17 as the for the population proportion. Which one I should use? Based on the distribution. If the distribution is symmetric, all of them will be always the same. They will be the same. But if the distribution is highly skewed to right, highly skewed to left, you should use median, or you can use mode. But the mean get affected by the outliers. So estimate the posterior mode under uniform 0, 1 prior and 7 successors. Keep in your mind the uniform 0, 1 is equivalent to beta 1, 1. So uniform distribution actually is exactly beta distribution with alpha is 1, beta is 1. Alpha is 1, beta is 1. This is a relationship between the uniform and beta distribution. And having 7 successors, y is 7, number of failures is 43, so n minus y is 43. So if I'm interested in calculating the posterior mode, it is alpha star minus 1 divided by alpha star plus beta star minus 2. And using uniform 0, 1 or beta 1, 1, and number of successes 7 and number of failures 43, it gave me beta posterior or posterior distribution beta with number of successes plus 1 as alpha star and number of failures plus 1 as beta star. So I plug in these values in the formula, I get 0.14. And then estimate the posterior median under uniform 0, 1. Under uniform 0, 1, it is the posterior distribution is beta with 844. So I plug in these values in the formula, you get 0.149. So now we covered 2 cases. No information available about the population proportion, which is using uniform, and there are some information available used the beta distribution. Maybe we are interested in variance. So maybe I would like to calculate the posterior variance. Calculating the posterior variance is one of the summary of the spread of this posterior distribution. The larger the posterior variance, the more uncertainty we still have about the parameter, even after learning from the current data. So the variance of beta distribution is this one. From where you got this formula? From the table of the distribution. This is the variance of the beta distribution in general. If you work with the posterior variance, this one will be star, 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 and so on. So for our motivating examples, we use beta 1040 as a prior, and n is 50, and y is 7. So, and the posterior distribution again is beta with alpha plus y as alpha star, beta plus n minus y as beta star. So with the posterior variance, you plug in all this information, you get 0.00014. This is the posterior variance. If you'd like to get the posterior standard deviation, take the square root of these values. So let me write it down if you want. The posterior standard deviation is the square root of 0.00014 if you are interested in the standard deviation. The posterior variance, some comments about the posterior variance. The posterior variance is smaller with an informative prior than with non-informative prior. It is expected. Because if non-informative prior means I have no information available about the population proportion. I didn't add any more information to the estimation. I didn't add any information in the Bayesian, in the posterior distribution. But for the informative prior, it means I added more information. So this is why for sure the posterior variance will be smaller when I use informative prior compared to the non-informative prior. And the posterior variance is smaller than the prior variance all the time, except if this is your case. If this is the likelihood, take the shape, and this is the likelihood, this shape, the posterior will be something in between. So when you look at this variability of the posterior, it will be higher than the variability in the prior, and the variability in the likelihood Why? Because you look at the peak, the height of this peak is smaller than the height of this peak. So this means the variability here is smaller, variability is smaller compared to the variability of the posterior. But in general, the posterior variance should be smaller than the prior variance, except you have this case. Let's calculate the prior variance and the posterior variance under beta 1040 and see which one is smaller. Under 1040, the posterior distribution is beta with alpha star 17, beta star 83. So the posterior variance, equal alpha star times beta star divided by alpha star plus beta star times alpha star plus beta star plus 1. So this one equal 17 times 83 divided by 17 plus 83 square times 17 plus 83 plus 1. This value is 0.001397. This is the posterior variance. Let's calculate the prior variance. The prior variance for the beta distribution, how much variability in the beta distribution? 1040. Prior variance equal alpha times beta divided by alpha plus beta square times alpha plus beta plus 1. Alpha is 10, beta is 40. So it will be 10 times 40 divided by 10 plus 40 square times 10 plus 40 plus 1. This value is 0.003137. This value is higher than this value because the prior variance is higher than the posterior variance all the time, except the case I showed you. Let's calculate the prior variance and posterior variance in the case of uniform 0,1. In the case of uniform 0,1, the posterior distribution is beta distribution with alpha star, number of successes plus 1, beta star, number of failures plus 1. So under uniform 0,1, the posterior is beta 844, and the posterior variance is 0.0025. Under uniform 0,1, which is equivalent to beta 11, I calculate the prior variance I got is 0.0833. When you can look at this one and this one, the prior variance is always greater than the posterior variance, except the case I showed you. Now, let's talk about the confidence interval in Bayesian, which is credible set. The Bayesian intervals called credible sets, and there are two types of credible sets. Based on what? These two types. Based on the shape of the distribution of the posterior. If the posterior distribution is unimodal, we use one of the methods. If it is bimodal, trimodal, it means we have more than one mode. So we use the other method. So let's look at the first method. The first method, equal tail posterior credible sets. The endpoints of the 95 equal tail credible set are the 2.5 quantile or 2.5 percentile and 97.5 percentiles of the posterior distribution. See, we always use the posterior distribution. So how do I find the lower limit and upper limit of the credible set? You use R function. You use Q beta. So this is a graphical representation of the posterior distribution with alpha star 17 and beta star is 84. We need to find these two limits, the lower limit and upper limit, and in between, the area under the curve is 0.95. So after we get these two limits, Q1 and Q2, I will say with 95 probability, because I'm working with the posterior distribution of the population proportion. With probability 0.95, the population proportion is some value between these two. So I use P beta, and I ask for the two quantiles from the beta distribution with alpha star 17, beta star 83. It gave me lower limit, upper limit. So now I can say with 95% with 95 probability, the population proportion of students who will quit school, if we raise the tuition by 20%, will be some number between 10%, 25%. So by R, calculate the 95% credible equal tail credible set if instead a uniform prior is used. So, and see which one is narrow. For sure, the one under beta is narrow. Why? Because it has more information. So under uniform 0, 1, which is equivalent to beta 1, 1, the posterior distribution is beta 844, and I use Q beta function. It gave me these two limits. So the credible set is 0.07, 02, 0.26, 205. If I compare this one to this one is more narrow, because this one, the posterior distribution in this case has more information. It means less variability. It means less uncertainty. It means more narrow. So the credible set under uniform or prior is wider than the credible set under beta, because this one has some information added to the estimation. So the posterior distribution under this case has less variability, less uncertainty, or more information. That is because the posterior distribution under this beta has more information about the population parameter compared to the posterior distribution under the uniform distribution. The other method is used when the posterior distribution is not unimodal, like this distribution. If my posterior distribution is this one, it is not unimodal. Is like this one is not unimodal. This one is trimodal. But if it is like this one, only one mode, you can use the first method. But for this case, for example, it has two modes. It's not necessary to have the same height. So if I use the equal tail and I asked R to give me the two quantiles, the 2.7 percentile and 97.5 percentile, when I look at these lower limit and upper limit, I will find many values in between. Some of them has very low likelihood. These values has very low likelihood compared to something out of the confidence and the credible set. So this one is not good. If using the equal tail is not good in this case, because again, some values inside the confidence and credible set has lower likelihood compared to the some values out of the credible set. What should I do? You should use the other method. That in this other method, we imagine that there is a straight line that go down, 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 and then look at the intersection. Like for this case, the intersection is these 4 points. And then calculate the area under the curve and between these two values. And the area under the curve between these two values, if the sum of the two areas is 95, if you are interested in 95 credible set, so this is the credible set. It is not one, it is two credible set. Yeah, I know. So the union of these two areas will be the credible set. Let's say this one is Q1, Q2, Q3, Q4. But if this one is not enough, is less than 95, you keep dropping the straight line until you hit 4 points. In this case, the area under the curve between these 4 points between these 2 points plus between these 2 points, the area is 95%. So let's say this one is Q1, Q2, Q3, Q4. So the credible set is Q1, Q2, union, Q3, Q4. This method is called what? This method is called highest posterior density region, or HPD. So the posterior density at any point inside such HPD region is greater than the density or the likelihood at any point outside. So the union of these two areas is the credible set. This is how to find the, whatever the number of modes. If you have 3 modes, you keep dropping the straight line until you get the sum of the area under the curve is 95. Maybe you get the area under this curve on, under this part only is 95. You stop. But if not, you keep. So maybe when you reach this one, the sum of the areas under the curve for these 3 intervals, maybe the 95%. So in this case, you should have some notation like Q1, Q2, Q3, Q4, Q5, Q6. So the union of these 3 areas is the 95% credible set, or 99 based on what you are interested in. This is the second method. So the interpretation of Bayesian interval, again, the posterior distribution represents our updated subjective probability, because we update the prior distribution with the likelihood, updated subjective probability distribution for an unknown parameter. The 95 credible set can be interpreted as the probability that the true population proportion parameter pi lies in that interval is 0.95. This is the statement we cannot make in the frequency approach. For example, if the beta is 1040, is our prior beliefs or knowledge about the parameter pi, then after seeing our data, we would believe that the probability of pi between these two values is 0.95. This is the statement that the frequency approach cannot make. So it is not confused in this case. There is no confidence level. We can say with probability, the population proportion is between, you get the two values using the Q beta function in R. Testing. In frequency approach, we calculate something called p-value, and based on the p-value, we fail to reject this one or reject this one. But in Bayesian approach, we can find the probability of H0 and the probability of HA, because we have the posterior distribution of the population parameter. So the area under the curve of the red one, the posterior, the area under the curve is 1. So I can calculate the area under the curve less than 0.10 and the area under the curve greater than 0.10. And those are the two probabilities of the two hypotheses. So I can use p beta function, and I ask p beta to give me the area under the curve less than 0.10 for the posterior distribution with alpha star 17, beta star 83, and it will give me the area under the curve less than 0.1. This one. This area is what? This is the probability. This one is the probability of H0. The probability that the population proportion is less than 0.10, is one of the values less than 0.10. And this one will be the probability of HA, the probability of the alternative hypothesis. Now I can compare the two probabilities and take my decision. So we would conclude that the probability of pi is less than 0.10 is 0.019. What is the probability of the other one? The probability of the other alternative, which is the probability of HA, that pi is greater than 0.10. This is very simple. 1 minus the probability of H0, which is the probability of pi less than 0.10. So this one is 1 minus 0.019. This one is 0.981. So now I have the probability of the alternative as a probability of H0. So now I can compare these two and take my decision. And you can go back to the frequency approach and see it have the same conclusion or not, because our conclusion now is what? Our conclusion is probability of HA is very big compared to the probability of H0. This one is 0.98 and this one is 0.019. So we will go with the HA, or we can decide that HA is correct with probability 98. But the frequency approach cannot give us this kind of statements. Frequency approach is based on something called p-value, which is a very big debate nowadays about using p-value. So it is not probability of H0, it is not the probability of H1. So let's do the same thing. Instead, using uniform prior, instead of using beta distribution as a conjugate prior, use uniform distribution and calculate the probability of H less than 0.1. If I didn't add any information to the current data, the probability of H0 will be 0.13 and the probability of H1 will be 0.86. Still, the probability of H1 is much, much greater than the probability of pi less than 10. So our conclusion is the alternative hypothesis is correct with some probability 0.89. It means if we did the experiment, if we surveyed all the students at Virginia Tech and calculated the population proportion pi with 0.89 probability, it will be something greater than 10%. This one is small, the other one is a big one. So the alternative has a bigger probability. So with 89%, it will be some value greater than 10%. And I remember from the frequency approach, we failed to reject H0. It means less than 10%. So guys, if you have any question, please let me know. I will be more than happy to answer any question you have. So next, we need to practice on a statistical software R again. Need to practice on R. And also, we need to know how do we predict in Bayesian approach. Thank you so much. Have a great day. And see you next week. Thank you.